Okay. No, let's try this thing. Okay, can people hear me through the mic? I think so. Okay, let's start off with any logistical things. First announcement, I sent it out on the email. I like to have a pizza with the prof every semester because I do like to, get to know some of you guys. So there's a sign-up sheet outside my door. If you would like to do this pizza with the prof thing with me, it will be tomorrow. The pizza will be tomorrow at noon. But there's only room for a finite number of people. I have a sign-up sheet outside my door. Okay, if you're interested, go and sign up there. And yes.
So you mean to imply that
the sheet has not yet been filled up. Okay, so I encourage you to go do that if you're interested. Any questions about that? Okay, good. Any other logistical questions right now? We got an idea. So there was a question earlier about the midterm. That will be, I think we said April 25th. There was some confusion about when this programming assignment was due, but it was the day I wrote on the assignment itself, which is the 18th. So there shouldn't be any confusion there. Any questions? Yes?
About that homework. What exactly are we trying to do?
Okay, so let's see. Let me start off with the problem of the day. Actually, let me start off with the, let's talk about the programming assignment. Okay, and that will probably, let's start off with this thing. So what is this assignment about? This assignment is, we're talking about backtracking. We introduced it last time. Your goal this time is to write a program to solve a famous NP-complete problem. Let me come down like this. Your goal is to solve a famous problem called the bandwidth problem on a graph. What is the bandwidth problem on a graph? You are given as input a graph, which we have here on the left. Okay, the vertices are numbered 1 through 8. Okay, it's got edges between certain pairs of vertices. And your goal is to find an ordering of the vertices on the line such that no edge that the longest edge is minimized. We're going to put the vertices, at points on the, on a number line. 1, 2, 3, 4, 5, 6, 7, 8. Okay? The length of an edge is the number of vertices it spans. So you could view each one of the edges in this drawing as being of length 1 or of length 0. Depends upon how you want to count it. Okay? And the goal is, given as input a graph, find an ordering of the vertices so that we minimize the length of the maximum length of any edge. Does everybody see this? In this drawing, what is the maximum length of any edge? From 1 to 8, right? Which, depending on how we count, that's probably 7. Okay? And there was a way to rearrange or permute the vertices so that, in fact, the edges could be shorter. And our goal is input a graph, output a permutation, such that the edges are as short as possible. Okay? Any questions about that? Yes? We assume it's an undirected graph. This is an undirected graph problem. Exactly right. Okay? And why would anyone care about doing this? Before we actually do it, you may ask, well, why does anybody want to do this? And there are at least it's one of these problems that tends to come up surprisingly often. The two stories that I think are most convincing, one of them has to do with linear algebra. Okay? You guys may remember there was a time in your life when you did, you solved systems of equations and Gaussian elimination and multiplied matrices and things like this. It turns out that for a lot of these algorithms, if you have a matrix where all the non-zero terms are near the main diagonal, okay, you can do all of these things a lot faster. So one of the big businesses of using high-performance computers is to do these kind of linear algebra computations. And one of the first things they do before they do these computations is see if they can rearrange their matrices so all of the elements lie near the diagonal. And that, I claim, is exactly the bandwidth problem. Okay, if we think of an edge being between any pair of elements that has a non-zero value in the matrix that is best for doing these things is the one where you have permuted the rows and columns so that everything lies near the diagonal. Any questions about that? Another one that I think is also going to sound compelling is this is sort of the mother of all VLSI circuit layout problems. Okay? Fairly often, if you think about how circuits are designed, you look at your chip, if you looked inside of it with a fine enough microscope, you would see different units that were designed. There were adders, there were clocking signals, all kinds of different things. And there was some program that laid these things out on the chip so they could manufacture it. There was a logical circuit an electrical engineer designed. It had to be slapped down on a piece of silicon to manufacture it. What would you want? What governs the speed of your computer? Why you have that clock rate thing on your computer, right? And that the higher the clock rate, the better it is. You want more megahertz in your computer. What is it that limits how fast things can be computed in a circuit? Yeah? A lot of the issue is going to be the distance between things that have to be connected because the signal has to flow along this wire. And so in some sense, one problem that is an important circuit layout problem is given a bunch of circuit units that are going to be connected by wires. How do you lay the circuit units out on a chip so that the wire length is minimized? The length of the longest wire is what governs the clock rate, actually. Okay? So it becomes basically a bandwidth-like problem. Any questions about that? Those applications should be convincing. Okay? So this isn't a Skeena-only problem. This is a real problem. Any questions? Okay, yes?
Can you give just a different example graph?
Okay, so you're saying you want a better example graph. That seems like a reasonable thing. Let's see if we can construct a graph that might be more interesting. Okay, so let's look at a very special example graph. What about if the graph was completely connected? Ka-chunk, 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 ka-chunk. Here I've got 5 vertices, and every pair was connected. What is the best permutation to minimize the length of the longest edge if you've got a complete graph? Anybody? Yeah?
Well, in some way or another, since the graph is completely connected, whatever vertex we're calling number 1 and whatever vertex we're calling number 5 have to be connected.
Right. Does everybody see that if you give you a completely connected thing, there is no way you can avoid having an edge run from all the way to the left to all the way to the right, right? So this is another example, but it's not an enlightening example, except to note that there can be many, many different solutions here that will give you the same bandwidth, right? Any permutation would do the job. So in your problem, do I want you to give me all permutations that yield minimum bandwidth? No, because you might it might be an n factorial possible answers. I want you to give me one of them that yields minimum bandwidth. Let's look at another example. Okay, what if, let's say, my graph was a star? Okay, a star graph where I've got one vertex and I go ka-chunk, 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 ka-chunk. What would be the right layout of a star? Can anyone think of what would be you've got a vertex here where you've got n vertices, let's say n minus, let's make it n leaves and one star, one center point. What would be the right layout for this one? Yes? The thing you would really like to have is the center and then everything sort of radiating out like this. Does everybody see that? If you have a star, the longest edge, if you put the center of the star in the center of your permutation, is going to be like n over 2, right? Whereas if you put it at one end, it's still going to be n minus 1. Okay? Any questions? Are those enough examples for you?
I think I get it. It's more of a spatial thing than an actual. I thought it was like n plane.
Well, it's an edge length in a world where you're nailing the vertices down to numbers 1 through n, integers equally spaced. Okay? So it's a combinatorial thing because I'm telling you where the vertices got to be drawn, but you've got to assign which graph vertex to which spot on the line. They always have to be done in a line, you know, on the integer points from 1 to n, one vertex per point. Any questions about that? Okay? Any other questions about what the bandwidth problem is? If you do not understand what the bandwidth problem is, you have no hope of solving it. So make sure you understand it, and if you have any specific questions about it, okay, let me know. What about a cycle? Let's try, here's an interesting example. Suppose I give you a cycle. Can anybody give me a good layout of a cycle? Okay, so this, let's say vertex 1, 2, 3, 4, 5. Yeah? Does anybody have a layout? Yeah?
No matter what layout you have for a cycle, it will always have bad edge length.
You will say it will always have a bad edge length? I am not, first of all, the question of how bad is it? Okay? So let's just think if we can come up with a layout here. Maybe I didn't think this thing through. Part of me wants to say, if I do 1, skip something 2, skip something 3, skip something 4, skip something 5, and now I come back and I put 6, 7, 8, 9. Let's say it's a cycle on 9 vertices. Now how long, what is the length of my longest edge? My cycle's going ka-chunk, 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 ka-chunk. It's actually not that long. I think the bandwidth of a cycle is only going to be 2. Maybe there's a parity issue here, right? But does everybody see that a cycle does not have a long edge? Okay? And you say, oh, how do I be smart enough to figure that out? You don't be smart enough. Your program has to be smart enough to figure it out. Okay? Any questions about that? Okay? So the input is a graph. The output is a permutation that minimizes the length of the longest edge in the drawing. Any questions? Okay. So what do I want to tell you about this problem? Okay. First of all, this problem is an NP-complete problem, meaning that there is no fast algorithm in the worst case. Okay? It turns out to be, in some ways, a very NP-complete problem. Now, that's not a technical term. But what I will tell you is that even for graphs that are a very special class of trees, this problem is hard. Okay? So if any of you find an algorithm that runs very, very fast, I will assume your program is wrong. Okay? You should assume your program is wrong. Okay? Because we're looking for a program that is right in all cases. Okay? The input for any graph has to return to me, if you're willing to wait long enough, a solution to the problem. Okay? You don't get points for something that is fast and almost a solution. Okay? Any questions about that? Yeah. What is the limit on the time? You will be allowed to run it for 1 minute on your computer. So I don't want to know the running time of your program. I want to know what is the largest input files. What input files are you able to do in a minute, and what input files are you not able to do in a minute? Okay? And what is going to happen with an exponential time algorithm is that your algorithm, you'll run it on the first file, you'll sail along, it'll go like this, done, 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 and you keep running it on larger examples, and then you'll hit return and it'll go, spit out an answer, and then you go to the next largest size and it will never finish. There will be a sharp distinction between the sizes your program can handle and the sizes that it doesn't handle. That's why my threshold of success is, what is the largest of my input files of each type that you can do in 1 minute? Okay? Any questions about that? Yes?
So it's going to be one large component. It's not going to have like subgraphs that are disconnected.
Well, is it going to have different disconnected subgraphs? Well, let's think about it. Do I make you any absolute promises? I don't think I make you any absolute promises. Now, of course, what would you do if they were disconnected components?
I would ignore them.
You would ignore them? I wouldn't ignore them because, but what would I do with them? I would solve them independently, which is what I think you want to say. Is that okay, that's better. Okay, ignoring them sounded willful. Okay? But if you had different disconnected components, note that you would want to have the disconnected components appearing next to each other on the line. You don't get any points for interleaving a disconnected component. Does everybody see that? So that might be an argument that you'd better check to see whether or not the graphs are disconnected. I don't think I'm deliberately playing a trick on you, but that's an example of one thing that you might want to do. Okay? Knowing what the components are and what the structure of these graphs are is probably helpful. Okay? Any questions? Yes? Okay, what is the optimum time for doing this? Well, what I will tell you is if you can blitz through all my examples, okay, in a couple seconds each, you are not doing something right. Okay? I think I believe that. Or you better argue with me if you are. Okay? What I'm trying to say is the following. Some people are going to get it in their head that's saying, certainly, okay, the highest, I saw from the star that the highest degree vertex has to be in the center. Right? When you add a star, the highest degree vertex has to be in the center. So what my algorithm is going to be, I'm going to find the highest degree vertex in my graph, put it in the center, put its neighborhood over here, okay, and then look at the other vertices and put them down. And that'll be my answer. And that algorithm will be fast. It will run very quickly. The only trouble is it will be wrong, because it is not necessarily true that for every graph, that's what the optimal solution looks like. So that's what I mean by this. If you're not using backtracking and not searching through possibilities, you are presumably doing something wrong. Okay? Any questions about it? Yes? What does NP stand for? It stands for non-deterministically polynomial, which we will discuss what that means perhaps at the end of the semester. Okay? Turns out it's not that enlightening a thing unless you take like a automata theory, the theory of computing class. It has to do with certain kinds of Turing machines and things that are relatively irrelevant to what we're dealing with here. P stands for polynomial, means there's a polynomial time algorithm. NP, if you want to think of it as not polynomial, that would be a better thing for it to mean. Okay? But that's what it means. Okay? Any questions? Yes? That means that there is, with the appropriate fine print at the bottom of the page, which we will discuss at the end of the semester, that is, there's no fast algorithm for this. No worst-case polynomial time algorithm for this. Any questions? Okay? So what do I want you to do? I want you to write a backtracking program for it. Let me give you a correct algorithm for solving this problem. We agree that the winning solution is going to be a permutation of the vertices. Once I give you the permutation of the vertices, you could go through all the m edges in the graph, okay, and see where is it, how long is it in this particular permutation, and find what was the longest edge in that permutation. Does everybody agree that if I gave you a permutation, you could check what its bandwidth is, the length of the longest edge is, in that permutation easily? How many people know how to do that? How many people don't know how to do that? Okay? So what is my problem here? You are given as input a graph, an adjacency list structure of a graph G. I am telling you that the vertices are in an order. I have a matrix, an array, where I tell you that the permutation is 3, 1, 4, 7, 6. What other numbers am I missing? 2. Okay, am I missing anything else? 5. That is the permutation. You will now go through and say, gee, my edge is, here's an edge, 3, 6. Okay? Where is 3, 6? Well, vertex 3 is in position 4. Vertex 6 is in position 1, 2, 3, 4, 5, 6. The disk length of that edge is going to be 2 in this drawing. Does everybody see this? Okay. So give it, no, you don't see it, okay? The permutation is going to say, this says that vertex 1 is in position 3 of the graph. Vertex 2 of the graph is in position 1. Vertex 3 is in position 4. Okay? Now, if I give you an edge in the graph that is edge 3, 6, vertex 3 is on spot 4 on the line. Vertex 6 is on spot 2 on the line. The distance between absolute value of 4 minus 2 is 2. That edge with this drawing would give me a length of 2. By going through all the edges of the graph and testing them against a permutation in order m time, I can figure out what is the cost of that permutation for that graph. How many people see what I'm saying? How many people do not see what I'm saying? Okay, I didn't get as many yes, I see what you're saying that I would like. Let me try this again. Do people see that if I give you the permutation to check what the length of the longest edge is in that permutation, I just take every edge in the graph, find what the positions, by looking it up in the array, what the positions of those two vertices are, and I subtract them and take the absolute value. The longest of these over all the edges of the graph is how good this permutation is. Does everybody agree that if I give you a permutation for a particular graph, you can tell me how long the edges are? Who agrees? Who does not agree? Now then, to finish your thing, all you need to do is to enumerate all permutations. For every one of the permutations, for n factorial permutations, you construct it. Now in process permutation, what do? You go and see for the graph how long the edges are. If this is better than any permutation you have seen, set it aside. If not, go and find the next permutation. We saw last time how to construct all permutations, right? Instead of printing them out, test them. Okay? And that, I claim, is a correct program for this problem. That should not be hard. Any questions about that? I can also tell you it will be slow, okay? But it will not be, it should not be conceptually hard, okay? Any questions about that? Okay? Making it faster will be where we start talking about pruning, and that's what I want to talk to you about today, okay? But it should be clear that in the grossest part of this assignment, this is now not hard, okay? Any questions about it? Okay, in fact, if you're saying, oh, I'm confused, I don't understand this backtracking stuff, what do? The first thing you do is get a working program to construct all permutations. Once you have that, it should be trivial to construct a correct program for this. Okay? Although, I warn you, it will be slow. Okay? But slow is better than nothing. Okay? There's a big leap between nothing and slow. Okay? Yes? Well, okay, so is there a better way? What is going to be better about it? Right now, what I'm telling you you're going to do is I am saying systematically construct all n factorial permutations, every single one of them, and test every single one of them. Now, maybe, if you're clever, you don't have to test every single one of them, okay? And I will show you with the pruning how you can figure out which ones you may not need to test. And the more you do not test, the better off you are. That is where the money is in this problem. Any questions? Okay. Any questions? So let me just go through again the rules of the game here. Okay. And I want to make this clear. And then I'm going to talk about pruning. First, this is one you do not work with your partner, okay? You want to talk to your partner a little, that's fine. But I think this is one that it's important that you learn how to program by yourself and make sure you understand it, okay? So no partner. Again, if you do not understand what the bandwidth is, okay, of a graph and how you compute it, okay, this is going to be hopeless, okay? Make sure you understand it, okay, or else nothing else to do. Okay? I give you a bunch of examples, okay, of graphs for you to try. I encourage you to start with the smallest files and then work your way up to the biggest files as you see, once you start seeing where it starts taking time. The wrong thing to do is to say, oh, I'm going to try a big file and watch it for the next week and a half, okay? You start with something that you can finish within a couple of seconds, okay? Any questions? And then work your way up. Any questions about that? Okay? Again, I give you the files on the web page. You are not going to be graded on how fast you're on how clever you're on style. So, do you need to add comments to your program? No. Are the comments going to slow your program down? No. Okay? You can use the good practices you know about. Okay, they're there for a reason. But that's not what I'm caring about. Now, I'm going to let you use whatever computer you have access to. Okay? Now, some of you are going to say, I'm going to go use a supercomputer. I know how to break into the one at Brookhaven. And I'm going to say, don't waste your time. Okay? Any computer is as fast as any other computer on the scale of this. Okay? Recognize that your algorithm is going to be exponential. If my computer is 10 times bigger than yours, that means that you should be able to solve faster. You could solve a problem that is 3 vertices larger. That's what it works out to. If you figure that your algorithm is going to take something like 2 to the n time. Okay, I made that 2 to the n. If it's n factorial, it's even less. Okay? So the differences in speed between computers don't really matter. Okay? Feel comfortable developing this on your laptop. If your uncle has a faster laptop at the end you want to run it on, fine. But that's not really the big difference here. Okay? Some of you may say, I have a cluster of computers. I can use all cluster of them. And if you want to do that, that's fine with me. But it's not going to matter. Your cluster of computers is going to have what? 100 machines? Big deal. Your program runs 100 times faster. The issue here is going to be an exponential speed up by pruning. That is where the money is. Okay? And a mere 100 times faster computer isn't going to make any difference here. Any questions about that? Okay? Some people have asked me about what programming language they use. Some people say, can I program this in assembly language? You can program it in assembly language, but it doesn't make any difference. If you program it in assembly language, it will only be 10 times faster. That's not what you're looking for here. You're looking for the algorithmic improvement that comes from not visiting every permutation. Does everybody get that idea? Okay? What programming language should I use? Should I use C or should I use the one that I know better? C is faster, isn't it? Well, C is only 10 times faster probably than Java or Python or whatever else you would use. So unless you're using something that's pathologically weird language, I would recommend that you use what you know. Okay? Any questions here? Okay? If you're saying, I know all languages equally, I personally would use C. C is probably a little bit faster. But that's because I know C better, frankly. Okay? If you know Java better, you're much better off doing it in Java. If you know Python better, you're much better off doing it in Python. Any questions here? Okay. Okay. So what are we going to do? Again, I'm interested in knowing what is the largest file you can deal with in 1 minute or less of wall clock time. Okay, so you're timing this, that the precision of the timing is such you're going to be doing it by looking at a clock. Okay? And whatever can run in a minute is good. Anything that takes more than a minute is not good. Okay? Any questions? Okay? And again, what we're going to do is I am going to collect, you guys have to turn in printouts. I am going to be collecting the programs of the 5 fastest ones, and they will be subjected to the contest to determine who is the fastest in here. Any questions about that? Okay. So let me give you one more hints before we talk a little bit more about this. One thing I strongly urge you to do is to not optimize prematurely. Okay, what does this mean? Everything that matters at the beginning is how much of the search tree do you prune. Okay? Some of you may say, I can do backtracking by iteratively instead of recursively? Is that better? Okay? I strongly encourage you to do is to do what is focus on doing the search and pruning as much as possible. In the last few minutes of, the last day before you turn in your program, you might want to worry about some code level hacks to try to speed it up. Okay? What data, is there a way I can avoid doing this test or something like that? But your main goal is to maximize pruning. This is one reason why assembly language is a terrible idea, because the more complicated you make your program, the harder it will be to add pruning heuristics. Okay? And if you make it so complicated by adding all kinds of different pruning heuristics, you won't know which are actually helping you and which aren't helping you. So simplicity, cleanliness is important here. Any questions? Okay? Again, one thing that matters, I encourage you to think about what your data structures are. Okay? How are you going to represent the graph to make this as easy as possible for you? How are you going to represent the permutation to make this as easy as possible for you? Okay? Any questions about that? Okay? And I do recommend, has everybody ever heard the phrase, the acronym KISS? What does KISS stand for? Keep it simple, stupid, right? And it's an argument that you don't make things too complicated. Some students are going to come in here and say, I have made it where I've handled all kinds of special classes. I have a special way of dealing with stars. I have a special way of dealing with cycles. I have a special way of dealing with them if every vertex is of degree 3. And that program is going to lose, okay? The programs that are going to win are going to be the ones that use simple, powerful heuristics to prune by, okay? That are well engineered, that are well thought of. I will believe that the winning program, the shortest possible program to write here is probably 50-ish lines. The shortest reasonable program is probably about 100 lines. The winning program in terms of speed, I bet you, is going to be between 200 and 300 lines. And there will be a bunch of programs dragging up the pack that are about 600, 700, 800 lines. Okay, that's my prediction. You can prove me wrong. Okay? Any questions about that? Yes?
Are you going to be publishing a bar graph of program lengths?
I'm not going to publish well, we can take a poll at the end of the time and see how long people's programs were, and you'll see that's what it was. Okay? The other thing that I want you to be aware of, just again, is a little premature. Your computer, your runtime environment, again, I don't know what your development environment is, probably comes with something called a profiler. A profiler is a way to take a program and figure out where it is spending its time. Okay? Typically, you compile it in a special way, and then when you run it on an example, it keeps track of how much time was spent in each subroutine, or maybe even each line of code. Okay? And this is very, very useful information when you're trying to speed it up. What you will find is, when you do this, that 90% of the time in your program is being spent in a small number of lines of your program. And if you optimize the rest of the program, it does you no good, because that's not where you're spending your time, right? So it's important to know where the time is being spent. And one thing that I do is encourage you to, at the end, when you're doing the final tuning, run it through a profiler. In the beginning, you should be worrying about how much pruning you're going to be doing, okay? And that's less profiler dependent than just looking at the graph and thinking, how much of the search space can I knock out? Any questions? Yes? What is a profiler? A profiler is something that is probably part of your development environment that enables you to tell where what is your development environment? What? Terminal. Okay, the terminal. Well, if you're using C, there is something called prof or gprof. That is your way of doing it. Undoubtedly, who here has ever used a profiler before? A bunch of people. What are the names of your profilers? Somebody else. Yeah. Zombie? Okay, no. Okay, bottom line is there. It is there. Okay, if you can't find it, you Google profiler. You look in your profiler in language, space, whatever your development environment is, and something will be there. Okay? Any questions about it? Okay? Okay, we'll talk more about this over the next couple days, but classes, but I think that's enough to get you started on the assignment. Any questions? Okay? Now, the only thing is, I guess I haven't told you about, about pruning yet. And that's sort of what I have told you is where the money really is. Let's start to look at backtracking again. And now figure out how do we write decent backtracking programs. And for this, I turn to the problem of the day. The problem of the day says that you want to find out what a derangement is. What is a derangement? I always love that word, actually. A derangement is a permutation such that no item is in its proper position. What is a derangement on 4 items? Okay, let's think about it. Is the permutation 2, 1, 4, 3? Notice that in this permutation, there is no element I such that I is in the right its own position. Does everybody agree with that? Are there? Can anybody give me a derangement on 3 items? Okay, there's a permutation of 3 items. Yes? 3, 1, 2 is a derangement on 3 items. Does everybody see that? Can anybody give me a derangement on 2 items? I guess 2, 1, right? In general, some permutations are derangements and other permutations are not derangements. Okay? And suppose our goal is to print out all the derangements out of n elements. Okay? And all n element permutations that are derangements. Any questions about what a derangement is? Okay? Is that clear? Now, how do we find these things? If I want you to construct these things, the answer is, well, why don't we use backtracking? Now, what is it that you use? How do you take my generic backtracking program and make it do something? What are the 3 things that you potentially have to change or can change? Does anyone remember? Yes? Is a solution. Is a solution. Question mark. What's the other one? What are the other ones? Construct candidates. That's going to be done again. In general, we've got a permutation partially specified. And I've got to now figure out what are the candidates for the next one. And what was the last one? What was the other thing that I might want to do? Okay. This says, is something a solution so far? Construct the candidates. What was the other thing? Well, process a solution. Once I have something that is a solution, what do I do with it? These were the 3 choices that I had. I might go to the board if this is helpful. How do we now, so again, what is it going to be doing? Backtracking, remember, said, given the contents of my array so far, is it a solution? If it is a solution, process it. If not, construct all possible candidates for the next spot, and then one by one try it and then backtrack. Now, I want you to use that backtracking procedure to find all derangements by using this thing. How can we now, what should we tell each of these 3 subroutines to do in order to get derangements out of it? Okay, any ideas? Okay. How should we represent the solution? What should our array be? How many elements long? Our vector, our solution vector. You're saying it's n elements. And what is going to be, what are the possible candidates for each spot? Yeah?
Every number except for the position we're in right now. So position 1 should be everything except for 1.
Okay. And in general, what about position K? Everything except for K? Is that what all the candidates are for this position? Well, we also, yeah. You want to make sure it's a permutation, so you want to exclude the elements that are actually used here. Does everybody see this? So let's think about it. What are the candidates for the kth position? Basically, it should be the numbers 1 through n minus k. I'm not going to, these are sort of set minus difference things, not additive things. I don't want k because it's going to be a derangement. I can't have it here. And minus a1 dot 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 ak minus 1. Right? This says that the candidates for the kth spot are all the numbers, integers from 1 to n, less k, less anything I've used so far. Does everybody agree that those are the possible candidates for this spot? Right? What is it? How do I tell whether or not my array is a full solution yet? Okay. Yeah? Right, so if k equals n, this you may have to look at the notes to see why that is k equal to n, question mark. Right? If I have filled up the first n elements of this array, and at each point I had a new element that hasn't been used before, and no element is in its proper position, I have a solution. Right? Does everybody see that? And what do I do when I have my solution? What do I want to do? Okay? Well, what do you want to do with the derangements? Maybe you want to print them, right? Perhaps maybe we would say print. Okay? And print, a sub 1 dot 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 an. Right? Does everybody see that this will construct all the derangements? Okay? How many people see it? How many people don't see it? Any questions about it? Is there any other way we could have spread the work? Okay? Is there any other way we might have partitioned the work between these different jobs? Okay? So let me try another approach, which maybe I'm going to see. Do I get another? Okay, even get another color. What if, let's say, I decided another way I could have done this might be to let whatever I want, okay, be a, whatever I want, let's say not check, to see, not prevent you from having the kth element in that position. And then when I process the solution, before I print it, I could say test if A is a derangement. If so, then print it. Do you kind of see what I mean? Suppose if I don't do this, I'm constructing all permutations. Does everybody see that? Another way I could have done this computation would be to construct all permutations, and then in process solution, I could then test to see whether this was a derangement, and if it's a derangement, then print it. Okay, does everybody agree that that's also a correct program? Yeah?
I agree it's correct. I just think it's slower than what we had.
You think it's slower than what we had before. Why do you think this is slower than what we had before?
Because we aren't pruning the permutation tree at all.
Okay, you're saying because we're not pruning the permutation tree. Okay, yeah? Okay, so it's a question of, here the real question is, how many permutations are derangements compared to how many things are not derangements? Does everybody agree that if there are a lot fewer derangements than there are permutations, this way is going to be much, much slower than the other way, right? Now, so is this way I'm doing in black better? Certainly not. You should get more pruning the other way. Is it worse? Interestingly, it probably really isn't, because it turns out there's a lot of derangements. I think there are something like n factorial over e derangements. Okay? This is good. This is just going to mess with your head a little bit. Okay? In fact, the number of derangements turns out to be only about n factorial, as many as n factorial over e. What was e? Does anyone remember e? 2.718, which means that 1 out of every 3 permutations you encounter is a derangement, right? So in a big O sense, it's not really that much different. But certainly the black one is not a win. Okay? You're better off doing the pruning as quickly as you can. Okay? In this case, it won't pay that much dividends. Okay? But in general, this kind of thing will pay a lot of dividends. Okay? It's really a question of how many solutions are there versus the size of the search space. If you've got a lot of solutions, you might as well construct them all and test them explicitly. But if there's a small number of winning solutions, then you had better, then you would better prune the search to avoid that. Any questions about that? Do people, any confusion at this point? I think that's a good example. Any questions? Good. So let's talk kabunk, 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 kabunk. Okay, so let's now talk about a little more about pruning, where the pruning win is going to be very big if you use the right pruning and the right representation. There's a famous problem called the 8 queens problem. A chessboard is an 8 by 8 board. A queen on a chessboard, I don't know how many of you play chess, has this queen has the power to walk anywhere in a row, anywhere in a column, or anywhere on a diagonal through it. That is what this queen can move. And the 8 queens problem, or in general the n queens problem, says you've got an n by n chessboard. You'd like to put n queens down on it so that no queen can attack any other queen. Does everybody see that this queen right now, no matter where it moves, can't take out any of the other queens that have been put on the board? Okay? And in general, that's what the n queens problem is. And our goal is, given a chessboard, find a way to put down n queens, okay, such that none of them are mutually threatening. Okay? Any questions? What about, just think about it a little bit, for a 4 by 4 board. Here's a 4 by 4 board. Can anybody figure out how to put 4 queens down so that they don't attack? Think for a minute. I know he knows. That's why he's probably came up with that one. Think for a minute. Yes. How do you do it? First column, second row, you want to put a queen here. Second column, last row, queen. Does everybody see that these 4 queens, none of those queens can take each other out, right? Okay, any questions? Okay, so your goal is to figure out how to put the queens down so that they can do that. Okay? How should we represent the board? We've got an n by n board. What is the way to represent a queen solution? Yes? A matrix. So what do you want to propose? You want to propose, again, you say a matrix. I think what you're saying to me, since I keep telling you that in my backtracking, my solution is a linear array, it seems to me you want to put together an array of n squared cells. Is this kind of what you're saying? And what is the cell ij? What is a given cell going to represent? Each cell is going to represent 1 square on the board. Does everybody see that? And so what he's going to do is to take his thing, and he's going to number each spot on the board. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, ... Right? And what are the candidates for this spot going to be? What are the possible candidates for that spot? You say 0 or 1, meaning either a blank, I'm going to say, or a queen. Right? Does everybody see that? So let's think about your solution here. What is construct candidates? You're going to be telling me that at any point I put down as a queen or a non-queen. Is that what you're saying? When do we have a solution? Okay. Yeah? You're saying when we've put down 8 queens, okay, meaning when you've hit 8 Qs, you've got a solution. And that's only if, I guess, once you put down a queen, it's not always, your construct candidates is not always going to be a blank or a queen. You're going to be asking yourself in construct candidates, given that I have a current configuration with a certain number of queens on it in certain positions, now ask me, can I put a queen here or not? Right? Does everybody see that that logic has to be in the construct candidates? Right? Or I guess what you could do is keep constructing patterns of Qs, but somewhere along the line you're going to have to test to make sure none of the queens threaten any of the other queens. Right? And he's proposing, I think, are you proposing, to test it at the time of construct candidates. Right? Or I guess you could do the same thing I did before and go and build the whole thing and at the end say, oh, I've got 8 queens down. Do they not threaten each other? Right? Those are 2 different ways we could do it. We could keep putting down queens or blanks until we have 8 queens and then say, oh, do any of these queens threaten each other? If so, this was not a solution. Okay, let's backtrack. Okay? Or smarter would be to do the pruning now at the beginning. Okay? But how big is the search space that you're looking at? Here's what I'd be thinking. Okay, any questions about this way we're doing it? Now, this is not a great way to do it. Okay? Why is it not such a great way to do it? How big is that search space going to be? Yeah? Okay, so one part, depending upon how you do it, the way I think about these things, which is maybe not quite right, I think this is scary sounding to me because I am seeing an array of 64 cells, and at each point I've got a choice of a queen or a not a queen, right? So my grossest analysis says that this is something like 2 to the 64th possibilities. Now that's not exactly true because he's going to prune out anything that had more than 8 queens in it, right? But if we can come up with a more concise representation of a board for the special properties of this queens thing? Yes?
Can you just do an array that's 8 elements long, and each index would represent 1 queen, and the number in that index would represent what?
So one observation is to note the following. If we've got an n-queen solution, how many queens can be in any given row? Here I have the first row of my matrix. How many queens can I have in my row? 1. Does everybody see that? Okay? So now what he's going to be proposing is, instead of having 64 cells, which can be blank or not blank, okay, have an array of only 8 cells, each of which is going to be the column number for the queen in that. How big is that going to be? How many choices are there for each element here? 8. Okay? So what is the worst case bad size for this thing? That would be 8 to the 8, which is wildly better than 2 to the 64. Does everybody see that? Any questions at this point? Okay, about how we do the representation or anything like that? It's a good point of seeing some discussions, which is good, but I'm happy to take questions myself. Okay, any questions? Okay, so this is a much better thing, okay, because now I've got 8 choices for each, for each spot. 8 to the 8th is quite a manageable number to search through. Yes? Okay, so what you're really trying to tell me is no, 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 it's even better than 8 to the 8. Okay? Because once I put down a queen in the first spot, the claim is that I can't use that column again, right? So certainly, I am going to be getting away with not 8 to the 8, but it's going to be a permutation of the columns. So in fact, it's going to be 8 factorial. Is 8 factorial less than 8 to the 8? Yes. Is it wildly less than it? Well, but it's still, it's basically 8 factorial is the right answer here, right? So does everybody see that thinking about the solution this way? I cut this impossibly ghastly 2 to the 64-ish thing. Immediately is down to an 8 factorial thing. Okay, an 8 factorial, you know, your cell phone can do, okay, for you, okay, if you just didn't use it as much. Any questions here, if you kept it charged? Any questions? Okay? So what the representation is very important. You want a representation of the search space that is concise, that gives you the ability to identify when there is something that is a mismatch. Okay? She noticed that, in fact, instead of being 8 to the 8, it was 8 factorial, because this representation looked a lot like a permutation. Okay? And at that point, you can easily make the mental leap that that's what this is. Any questions? Okay? So how do you solve the 8 queens problem? Okay? I claim the following is my 8 queens code. Okay? The key work is, given is my construct candidates. Usually, I don't want to make a rule, but let's say usually the art of what you're doing is in the construct candidates. You know that if you are filling in the queen that is going to go on the kth row, okay, you want to find what are the minimum number of spots that you can possibly put a queen here. Okay, the smallest set of possible spots, smallest possible set of positions where you can put a queen down. Now, what is going to govern it? You already have your array A from 1 to k minus 1 details the positions of any queen. You're clearly going to blank out any columns where there is a queen. What is the other situation under which you're going to rule out a queen? Yeah? Diagonals. Is there a queen here which will threaten a square? If it threatens a square, this square is not going to be a possibility. Correct? So what does my construct candidates do? Basically, what I'm going to do is, okay, again, there are a couple of different ways you could organize this thing. What I'm going to do is, for each of the n possibilities for my next thing, I am going to go through, test whether or not there is a legal move for this. Originally, for column I, there is a legal move unless I find a queen that prevents it. I'm now going to go through all of the k queens, okay, that are already in my partial solution. If the jth queen is in the ith spot, well, position I can't be legal. Okay? If, okay, then there has to be the test of the diagonal situation. Under what condition? If this is spot J, and this is a queen in the, this is a queen in the ith row. Okay? For it to threaten me, it has to be somehow in the position J minus I. Does that kind of make sense? That, you know, if it's one spot, in the previous row, it had better be one diagonal from me. 2 rows up, it should have been 2 spots. 3 rows up, 3 spots. The key test is basically the absolute value of, okay, the queen, depends upon what row it is, okay, the row in the column, such that it threatens me. This is the condition. You can check that out pretty easily if you just rule it out. But basically, it's, you know, It's got to lie on a slope of 1, meaning it's got to be a certain number of columns over and a certain number of rows up. If that's the same, then it threatens me. Okay? Any questions about it? And if there is a way that I am threatened, okay, then this move is going to be marked as not legal. If the move after testing every queen is still legal, then I add it to my set of candidates. Any questions about that? Okay. Now, note that I could have sped this up perhaps a little bit by being a little bit more quick. Instead of having a for loop, okay, I could have had a while loop where once I had found a way to make the move illegal, I didn't look at any other queens. But note that that would not have affected my search tree. That only affects my time to generate the candidates. Okay? Where it really pays to worry about things is making sure that I don't test, I maximize the number of candidates I eliminate from consideration. Okay? Any questions about that? Okay? So that is construct candidates. Otherwise, what was the rest of my program? Kabunk. That's it. Okay? Is it a solution? Well, when I filled my array up with legal moves, I have a solution. And what did I do once I found the solution? I could have printed it out if that's what I wanted, but here I just wanted to count how many solutions there were. Okay? And when I ran this before on my ancient little laptop, okay, you know, I was able to go up to like n equal in a couple minutes up to n equals 14 by 14 board, and found 365,000 solutions to this. Okay? Any questions about that? Do you see that the key here was representation? What is the concise way to put the board down so I don't have to search through as many possibilities? And pruning. When do I recognize that a move will do me no good, cannot help me? Okay? And when that happens, I back up and immediately say, if I find that there is no possible way to put a queen down on this row, does it pay for me to look ahead another row and see if there's a way to put a queen down there? No. Any permutation with this prefix is doomed. Okay? So I'm not going to search through any permutation with that prefix. Okay? Any questions about that? Any questions about how the 8 queens works? Okay? This is a good example of a success of pruning. Any questions? Okay, let me show you about my favorite success of pruning, personal success. Okay, is a problem I worked on at one point. Another chess problem, okay, which had to do with putting pieces on a chessboard so that none of the pieces actually threatened each other. Okay? This is again, how many people, okay, hopefully people know, have seen chess before. You know that different types of pieces move in different ways. Hopefully you know the ways the pieces move. If you don't worry about it. It won't be on the final. Okay? But what is the point? In chess, you are given 8, each side gets 8 main pieces and 8 pawns. Forget the pawns. You get a king, a queen, 2 rooks, 2 bishops on different colors, and 2 knights. Okay? And the question is there a way to arrange those pieces such that every single square on the board is threatened? Okay? On this board, I can tell you right now with these pieces, 63 out of 64 squares are threatened. Which square here is not threatened? Okay, somebody else who didn't cheat. Okay, I'm going to guess you saw. Okay, look at it. Is there any square on this board that is not threatened by a piece? What's N means knight, okay? K means king, N means knight, okay? Is there any square that is not threatened? Okay. Who sees one? Okay. Anybody else? Yes. Left and down one. Top right rook. You mean which one? Up at the corner? This spot. Who's threatening this space? Ka-chunk, ka-chunk, ka-chunk. He's got it, right? That's not one's threatened. Which one? Does anyone now see which spot is not threatened? What? First row, second column. This one? Okay. Wait, first, top left. This one? Who's threatening this square? That knight, ka-chunk, ka-chunk, right? Which one is not being threatened? Now you can tell them.
Okay, it's the square that the top knight is standing.
This particular square is not threatened. Knight is the only guy who's not being threatened, okay? 63 out of 64 squares are being threatened, okay? And this one isn't being threatened. And someone noticed this back in 1849 and said that is there a way to threaten all of them? And for the next 125 years, people worked tirelessly around the clock to try to find a way to threaten all squares, okay? And the question is, well, not tirelessly, okay? But it became a question, is there a way to threaten all the squares using these pieces, okay? And in between, since 1849, people invented things called computers. And now we could think about doing a search, okay? This is the kind of thing that backtracking is looked for. Can we look through all possibilities to try to find an arrangement where every square is threatened, okay? So let's look at how we can do this with backtracking. The first question I always ask myself, how big is the search space? Well, if we are going to be simultaneously saying for the first king, okay, there is the king, there's going to be 64 possible places you put it down. And once you put the king down, you then figure out where should this queen go. There are 63 possible places for this king, because it can't be where the queen is. And then we're going to put down the red bishop, and the white bishop, and there's going to be 62 possible places. Basically, there turn out to be this many possible configurations of those pieces, okay? That's 10 to the 15th configurations. Back when we did this was about 25 years ago, that was a big number. Today, this is not such a big number. With Moore's law, computers get faster double what, every 2 years or something like that? What? It means it's gotten doubled by about a factor of 10 or 15 times since I was in grad school, which means that it's 1,000 times faster, 10,000 times faster, okay? So there's a big difference here, okay? But nonetheless, how can we search through this? I think of it as about 10 to the 8th things can be searched through comfortably. If you need to search through 10 to the 15th, you got to do pruning. Do we have to search through all possible configurations? One important thing to note is an idea called symmetry. Symmetry is the idea that if I took a board, if I took a chessboard and I turned it around and looked at it from your end, it's still a legal configuration chessboard, right? But but it would represent if we look at it from my perspective, turning the board around changes the position of the pieces, but if the number of threatening things hasn't changed. I'd like to not look at the same symmetrical thing each time. Does everybody see that? Okay? If I can avoid looking at symmetrical copies, that will save time. Okay? And so one way, so there are a couple of different ways to look at symmetrical copies. One idea, the simplest idea, might have been to say, wait a second. If I had a board here, my king is a unique position. If I put my king on the, if I put my king on the, always insisted it be on this side of the board, I would cover all possible solutions. Because if you told me the right solution had the king in this board, part of the board, I would simply rotate the board 180 degrees, and then the king would be down here. Okay, I don't think I said that very clearly. How many people think they see what I mean by symmetry? Okay, and you see the principle that I don't want to search for, I don't want to look at things multiple times. Okay? Can anybody think about the bandwidth problem for a second and tell me where symmetry might come into your bandwidth solution? Okay? Anybody else? Does anybody see where that, yeah? Does everybody see that if I knew that there was no possible, that once I had searched for all possibilities with the 3 in the rightmost spot, that is the same as searching for all possibilities with the 3 in the leftmost spot, because I just hold my bandwidth solution in the mirror, and it's done, right? Does everybody see that? So by adding one line of code to your program, you can cut your search space by a half, just exploiting this property. Does everybody see that? Your candidates for the first spot, maybe. You don't allow yourself to you have to figure out how do you canonically make it so you look at one or the other. You think about that for a second. But it really is limiting your candidates for the first spot, okay, to compensate for reflections. Any questions about that? Okay, so symmetry is a big idea. And when you do symmetry in a clever way, I'm not going to tell you how you do it, the search space goes down to 10 to the 12th instead of 10 to the 15th. So that was a factor of 1,000 or so by the time we got through doing this right. Okay? That was good, but it wasn't enough. How else could we do it? What is our basic goal? Our basic goal is we want to take a partial solution. Okay, these are some pieces. We put down a king, a queen, a rook, such and such. We'd like to know as early as possible whether or not the prefix we currently have, the set of pieces we've already put down, whether there is any hope of them leading to a covering solution. Okay? If we can prove that there is no way to no matter where, let's say the next thing we put down is a bishop. We still may have to put down a bishop, a knight, and a knight. Okay, I don't know how we did this thing. If I could prove that there was no possible solution, okay, to the whole problem based that had these pieces on those squares, the quicker I could figure that out, the better off I would be. Okay? So how could I do it? In general, what are the candidates? In general, what are the candidates for the next spot? Let's think about construct candidates. Suppose, let's say I have a king. You know, again, it depends how you want to put it down, but I'm assuming that my solution representation will be, maybe I'm going to put down a queen, a rook, okay, a king, a bishop, knight. Suppose I have put down a queen here, a rook here, and a rook here. What are the set of possibilities for my king? Okay, what's in my representation here? Well, what should my representation be? Let's stop thinking about it. Here I've got an array. How long should my array be? Okay, 8. You want me to have an array of 8. What is the number? What is the content of each cell in this representation? Okay. You're going to say it's going to be in a representation. It's going to be in a representation of 8, where the ith spot is going to be the ith piece in my collection of pieces, right? What are the possible values for the ith piece if I want to construct my candidates? Any one of the 64 positions on the board, which one should be possibilities? Should I use any number from 1 to 64? This is where some pruning comes in. What pruning are we going to do? It's any number from 1 to 64 which is not threatened by any of these previous pieces. Does everybody see that? If I put down any number from 1 to 64, then I'm in trouble. Then I haven't done any pruning, right? But I'm saying I can put a piece here, okay? Anyway, what is the situation? Is it that, is it okay? Actually, I guess if I'm threatened here, it's okay for me to put a piece down, right? So let's just think of it. It's not the 8 queens problem, right? I want to threaten every square on the board. Is there any limitation on whether or not which numbers from 1 to 64 I'm allowed to put it here? I can't put it on any place where I have one of my other pieces, right? So that's a little bit of pruning. Is there any other criteria by which I can prune? This might not seem obvious, right? Yeah? A place where it doesn't gain me anything. You might say something, well, it depends upon how many squares are threatened so far, right? Maybe you're saying that if I had threatened, so far, if I had threatened 27 squares, and I put down another piece, and now it only threatens a total of 22 squares, maybe that's a bad thing.
I was thinking more like you wouldn't put a bishop in a diagonal with a queen necessarily.
When you say that, I don't know that that's necessarily true. Because it might very well be that when you put it down, you have a bishop in the same diagonal as a queen because you happen to put a king there also. And that king would block it. So I don't know that that's a good pruning criteria. It sounds possible. Okay? What is a good pruning criteria? Notice the following idea. We know that each piece has a certain power, potentially, a certain number of squares it can threaten in the biggest possible case. A queen is the baddest piece on the chessboard. It can take out 27 squares. A king is perhaps the wussiest piece on the chessboard. It can only go to its 8 neighbors, correct? So what is an interesting point? Suppose, let's say, I have put down a certain number of pieces. Let's say I have put down, the first 7 pieces on the chessboard and not the king. And there are 9 unthreatened squares. Is there any way the king can possibly finish the job? No. Let me say that again because people didn't hear it. And this is the key idea here. Kabunk, kabunk, kabunk. Suppose, let's say, I had an arrangement. Let's say I put it down where my last piece was a king. The last piece I'm going to put down is a knight, and the last piece was another knight. How many pieces can a knight threaten? A knight can threaten 8 pieces, if I am correct, right? Okay? A knight can threaten 8 squares, and a king can threaten 8 squares. Suppose that at the time that I had a configuration, I have put down 5 pieces, and at this point I have 25 squares still unthreatened. Does everybody see that no matter what I can do with those 3 pieces, there is no possible way to finish the job? Okay? If I have my 3 knight, and king left to put down, and I want to finish a configuration that had 25 open squares, there is no possible way to do it. Okay? And I can immediately backtrack from this point. How many people see that? How many people don't see it? I know there's more of you out there. Okay? How many people don't see it? Okay? Does everybody see that depending upon the order that I put the pieces in, if I keep count of how many squares are threatened so far, there is a maximum more threatening power I have from my unplaced pieces. And whenever the amount of threatening power that remains is less than the amount of work to be done, I give up, right? Does everybody see that? If it takes me 10 minutes on each algorithms problem, There are 10 algorithms problems, and there are 90 minutes to complete the test. Can I complete the test? I give up. Okay, well, don't, okay? Okay? But in the backtracking, that's clearly the right answer here. Does everybody get that? Any questions about that? To see if you understand it, let's think about the pruning here. Which is the order that I should put my pieces in? Should I put them in order from king, from most powerful to least powerful, or from least powerful, which is the king, to most powerful? Okay? Let's think about it. This is going to end up making a big difference in the running time. Yeah?
In the example that you had before, shouldn't the king actually be able to, well, instead of threatening, it can also pick up the space. So there's a space that's taken up account for that.
Well, okay. So, I mean, sitting on a space does not threaten it. Okay, that's why that knight was the place that wasn't covered. It was sitting on a space, but it was still vulnerable. It still wasn't threatened. Okay? But what's the important point here? Okay? Does it make any difference if I fill in the pieces, my partial solution, from most powerful in terms of the number of things that can threaten to least powerful, or least powerful to most powerful? Which is the right way to do it? Okay, yeah? From most to least, right? Because I want to be able to prune as many pieces ahead as possible. The most number of pieces ahead is going to be possible when the pieces that remain are the weakest possible pieces, right? So it turns out that this is the kind of a decision that is going to make a big difference in your backtracking. Okay? Which is the order in which you start putting your pieces down. If you put the powerful ones down, you maximize the chance that you're going to be able to look at a position early and say none of these possible extensions can help. Okay? How many people get that idea? That is the kind of thinking you want to be able to do. When we did this, okay, we were able to use this backtracking and it eliminated 95% of the search space, okay, just by ordering the pieces in the right way. And again, in order to really get this working, we had to do even more and fancier pruning. But we eventually got this down to run in less than a day on a tiny computer of its day era, which by now, you guys would sneer at, okay? Any questions? Think about it.